Good. Sorry, I was on mute before we tried to start for the past 2 minutes. um, right. It's a great pleasure to be here. So I'm going to give an introduction to superselection sector theory. So I'm aware that the background of participants is very diverse. So I try to keep it as basic as possible, just to try to give you some idea of some of the main points. But if there are any questions, feel free to interrupt me. I don't think I can see the questions that are asked on Zoom, but we'll see. Hopefully somebody else has the same question in the audience, if that's the case. Good, so let me get started right away. If I can actually change, yeah, all right. Good, so this is a brief outline of my talk. We'll see how far we get today, but we already heard a few words about the Tor code, so I will actually continue with the definition of the Tor code because we haven't seen the Hamiltonian yet. And basically the Tor code throughout this series of lectures will sort of be my guiding example. So what I'm going to say works much more generally, but the Tor code is very nice in the sense that, first of all, it's very easy to define, and it is well, relatively easy to analyze it. But at the same time, it has some very interesting features. So it's a very good example to work through. But yeah, again, I want to stress that this whole setup is much more general. Right. So let me first give a little bit of a motivation of why I'm interested in these kind of questions. So we've already heard about this in the previous talk. So the main thing that we're thinking about is the classification of gapped ground state systems. And the approach that I will be taking, we will always work in the thermodynamic limit. So that's what Bruno already mentioned in the beginning. We take our system size to be infinite. Let's say a square lattice. We're interested in gapped ground states of proper Hamiltonian. So we define some dynamics. We want this to have some spectral gap. I'll say this maybe a little bit more precise later on. And we want to classify them. So it means we have some kind of equivalence relation between the different states. So I won't talk about this too much, but towards the end of the week, I will make this a bit more precise, what I mean there in our setting. So yeah, this is just some of the motivation. But the main thing I want to focus on is states with topological order, or in my case, what we call long-range entangled states. So again, topological order or topological states can mean different things to different people. So yeah, so I want to stress I work with so-called long-range entangled states, and a little bit different from the inverted states that we saw before. But anyway, back to with sort of the mathematics question. We have some sets of states. We have some equivalence relations. So of course, the first question that you ask as a mathematician is, can we somehow classify all these different equivalence classes? In other words, can we find maybe invariants to distinguish them? And of course, it would be very nice if this invariance also would have something to do with physics, right? I'm a mathematical physicist, so in the end, I'm interested in doing physics. So that's kind of the setup. Well, what we want to do. So let me first say, so why are these states that I'm going to talk about? Why are they actually interesting? So why should we care about these states with long-range entanglement? Well, one of the main features that got me interested in these things in the first place is that these states, they can host anyons. So anyon you can think of as a quasi-particle excitation. Again, I will use many different names interchangeably, depending on sort of your background. Quasi-particle means different things, particle means different things. But yeah, so I will use these kind of interchangeably. But the interesting thing about these particles is, well, we can, if you've done any quantum mechanics, you probably heard of bosons and fermions. So if you have two bosons, you interchange them, the state doesn't change. If you have two fermions, you interchange them, you get a minus sign. And the anyons are kind of a generalizations for this. So if you have two anyons, you interchange them, something non-trivial can happen. Right, so that's what we call Brady statistics, and we'll see later where this names come from. Right, so these anyons, they have quite interesting properties. And it turns out that these the algebraic properties of the anyons, they are captured by this very nice mathematical structure called the braided tensor C star category. And so actually in all our examples, it's even a modular category or a braided union category, right? So in one of Alexei Guitar's papers, there's a nice appendix on sort of explaining all the physical, or explaining this from a physical point of view. Right. So as I said, so usually people say the anyons are described by modular category. So the theory that I will describe, it does not give me quite modular in general, but it does include the examples. I'll say a bit more about that. Right. So if these words don't mean anything to you, braid fusion category, modular category, and things like this, don't worry. So that's throughout the week I will explain these notions. Right. So from a physical point of view, one of the reasons why people get interested in these kind of things is this topological nature. And so one of the consequences of this topological nature is that these systems, they are kind of robust against small perturbations. So you have a physical system, typically, if you want to do some measurements, you will not be able to make, your exact model system, right? But you will make, there may be some impurities in your system or something like this, some perturbation of your system. But yeah, because of the topological nature of these systems, actually the features that we're interested in, namely the anyons, they behave exactly the same. So they're not sensitive to small perturbations, and that's very useful for many things. For example, quantum computing would be one possible application. Right. Yeah. So sort of the main goal of this talk is, well, we have these kind of anyons, and we have some quantum state that somehow be related to these anyons, or rather the other way around. And as I said, these anyons, they should be an invariant. They should be invariant under changing the system by a little bit. So I said this category should describe all the anyons. So we want this category of anyons to be an invariant of the states that we have. So invariant of the phase. Right. So basically, the central question is: so given a physical system given by, let's say, a Hamiltonian, like we heard in the first lecture today, can I somehow find this category of anyons just from this very basic data? So I'm giving this a global Hamiltonian, and somebody gives it to me and says, okay, what are the anyons of the system, if any, of course. And then the second question, and I will come to the second part only at the end of the week, is this indeed invariant? So if I get a small perturbation of the state or a small perturbation of the dynamics, I do this whole procedure again, do I actually get the same category? Oops, sorry. Good. So yeah, I'm not going to go give a very historical overview. I also make some historical comments, but there are many ways you can approach this problem, and I will not go into all of them. Right. So, and I said I will only talk about the so-called non-chiral topological order. So this distinction is not too important now, just for the experts. As I said, I will focus on the basics. I will just try to work to a simple example. I will indicate how things can be generalized, but I will not go too much into detail because this will just be confusing if you see it for the first time. Right. Good. So this is more or less the plan. So we'll talk about the Tori code and the ground states, and then slowly we will build this category of superselection sectors or category of anyons. And in the end, I will say a little bit about classification problem. Good. So this is my only history slide, basically. So the approach that I'm going to take is what's called the Doppler-Haag-Roberts theory. So this goes back quite some time. So it originates in algebraic quantum field theory. So this is an attempt. It goes back to the 1950s or so. to sort of formalize quantum field theory in sort of an operating algebraic way. So the standard, so basically in that setting, you look at so-called Haag-Castle nets. So these are nets of zeta algebras assigned to each sort of suitable region of space-time. You have an algebra of observables associated to this, and that should be like things that you could measure physically in the system. And this is, of course, very, very similar to what we saw in the first talk, with Bruno's talk, where we had this finite number of sets, and we had this observable algebra just given by tensor points. Right. So the DHR theory attempts to capture well, we call charged sectors there, and in higher dimensions, this automatically leads you to the conclusion that all these charges, they have either bosonic or fermionic statistics, parastatistics, slightly more general. Yeah, so one of the main results in this field is what's called the Topological-Roberts theorem, and mathematically says that if you have a symmetric tensor category, it's always equivalent to the representation category of some compact group G. So we can think of this group G as sort of the symmetry of this system. Right, so I will not say too much into that, go too much into this. But in lower dimensions, things get more interesting because sort of the geometry of the space is different. And we can get more interesting, so these gradings with the annuals, as I said. And maybe for some people that are interested in conformal field theory, maybe they're familiar with the theory of conformal nets. Again, there is very similar techniques here, right? So that's where much of the motivation comes from our approach. On a technical level, it's quite different. In our case, our local algebras are just matrix algebras, and in these cases that I mentioned here, they are much more complicated. Right. So I think I've talked more or less about three things in the title of the workshop now. So I talked about topological phases. I talked about QFT, although probably the QFTs we hear about will be slightly different flavor than here. And there was one more, operator algebra. So my approach is really rooted in operator algebras. So unfortunately, I don't have much to say about homotopy theory, but sure we hear a lot about that in the other lectures.
Sorry, so there's a finite set on simple and I don't know that I know in Roberts theater, but there's a subtlety. Like I think that, like for example, for C2 graded vector spaces, it's not the case that it's from G.
Yeah. Yes. Yes. You're right. So in the Z2 grade, if I remember correctly, you actually you have rep G with you basically have also graded representation. So there's a special element in the yeah. You're right. I'm not being too precise here, but yeah. Thanks for the question. Good. Right. So I want to mention a few different approaches, but one of the main features of this DHR approach, one of the original motivations, is well, we have this grading. So this will tell us, what happens if we move these annuals around. So one of the main questions is, so how do we get these gradings? So I will say the DHR approach. So I want to advertise the talk of my co-author. We'll talk next week about sort of a more geometric based approach in terms of prefactorization algebras. Some people might find interesting. So you can hear about that next week. And if you cannot wait for it, you can already download the paper from the archive. There's also a more sort of axiomatic approach that really kind of tries to identify what are really the essential features, geometric features that we need to define this whole superselection sector theory. So this is another paper that I want to mention. Good. Let's finally get to the Torah code. Right. So I will work on the square letters. And again, as Bruno already mentioned, the we will assume that our degrees of freedom live on the edges of the system. So that's typical for the Torah code. So of course, you can just rotate everything by 45 degrees, and then you can see the edges as the vertices. But this is sort of the usual way it's done. So we assume that at each of these edges, we have a two-dimensional quantum spin system. Or if you look at the observables on that, it's just the 2x2 matrix algebras. Good. So let me introduce some notation. So most of you have probably seen this. I will need these properties later on. So let me just briefly recall them. Right. So this is the definition of the Power matrices. So just these three matrices. Right. There they are. So they're all self-adjoint. And they're all traceless. But first, the most important property is that you can very easily check for yourself, is that they anti-commute with each other. So if I took, so this is the anti-commutator, so sigma I, sigma j plus sigma j, sigma I. And you'll see here, going to get delta, so either the both two are the same, I get 2 times the identity, and otherwise it's a 0. So the main, in other words, they square to the identity. If I take two different ones, they anti-commute. And the last thing that's important is together with the identity matrix, we get a basis of the 2x2 matrix. So that means we can write anything in terms of this power matrix, and that's going to be very helpful because they have these nice properties. Good. So it's now time to introduce the dynamics. So we've already seen the quasi-local algebra. Of course, the quasi-local algebra in itself is not very interesting. It's going to be the same for any spin system that has like its qubits or its two-dimensional spins at the initial sites. Right? They always get the same algebra. So it's really starts to become interesting once we define the dynamics on the system. Right. So I'm going to define the dynamics by specifying these interaction terms that are called phi in Bruno's talks. And we basically have two different types, one for each bracket of the system. So it's just these 4 edges around the square here. So I hope my mouse is also visible online. Right, but we have this square here, and we have this bracket here. Sorry, this bracket here and the star here. So a star is just 4 edges coming out of a vertex. Good. So to these operators, for the star operators, to a star, I assign this operator. So I act with a sigma x power matrix on each of these sides here, these 4 sides. And here I do the same, but with the sigma z operator. Good. So for each star and each bracket, I can define an operator like this. It's easy to check by what I just said, that they all square to the identity, and all these operators commute. Right. So why do they commute? Well, the sigma j's and this sigma x's and the sigma z's, they of course anti-commute, what I just said. But if you go back to this picture, if they act on different sides, they commute because they act on different parts of the system. If there is some overlap, it'll always be an even number, right? So for example, if I take this here, right? So we have 2 edges in common, so I have to anti-commute twice. So I get 2 minus signs, which becomes a plus sign again. Right, so that's why they commute. And now I can define the dynamics. Namely, the local Hamiltonians are given in this way. So I give a finite part of the system lambda. I just look at all the stars are in there and all the brackets, and for each of them I put this term there. Right. So the phi's in Bruno's terminology would be these individual terms here. Right. So these dynamics are very simple, so-called the commuting projector model. The way I wrote it down is not quite a projector. I need to scale by a factor of 1.5 to get projectors, but good, that's not too important. But yeah, so they are very simple. That's very nice because it makes things easy to do. That's actually one of the reasons why we can actually do this explicitly. Yeah.
Sorry, like you mentioned it, the X Pauli matrix for the star and like the Z Pauli matrix for the bracket, or
yeah, it's a choice you can make. You can do it the other way around. Yeah, so I'm not sure if there's a standard convention. I always have to make sure I do it right, but I do it consistently. But yeah, it doesn't really matter if you choose which one you choose. Otherwise, you basically get a dual. Yeah. Maybe I should have said this earlier, but this is a special case of what's called the quantum double model, also introduced by Kitaev. So you can define this model for any finite group, or even any I believe quasi-triangular Hopf algebra, if I remember correctly. But of course, the definition is much more complicated in that case, so I will not do that. But this is the special case corresponding to the easiest non-trivial group, Z2. Right. Good. So we heard about ground states in Bruno's talk. So we want to find out, what are the ground states of this model? Because in the end, we're interested in classifying ground states. Well, phases. Right. So I want to prove this lemma first. Right. So yeah, suppose we have some operators bounded from above by the identity. So that just means that 1 minus xi is a positive operator, so it's positive eigenvalues. Positive spectrum, sorry. And suppose there's a unique state such that omega of xi is 1 for all xi. So if there's some state that has, so this condition uniquely specified states. If that's the case, then omega is a pure state. I realized I haven't said what a pure state is. So a pure state is just a state that you cannot write as a non-trivial convex combination of two different states. Right. So that's one definition. Another definition, that's the one that I actually use here. If you have some positive linear functional, so positive in the sense that Bruno mentioned earlier, that's majorized by the state, then it must be a multiple of the state. That's another way of saying the same thing. Good. So let's assume that we have such a functional. Right, so this is a positive operator by this assumption. This is a positive linear functional, so this is positive. It's bounded from above by assumption by this, but omega of xi is equal to 1. So this is 0. Right. So omega is a state. So in particular, it's normalized, meaning it takes the value 1 from the identity operator. Good. Right. So this can only be true if phi xi is equal to phi I. But from the uniqueness assumption, this means that this must be a multiple of the other one. This concludes that it is pure. Right. So maybe this is a good point to say. So why would we care if the state is pure or not? So later we're going to look at representations, and if you take the GNS representation, as it's called, of a state, I will come back to this later. You'll get an irreducible representation. So we will get into irreducible representations from this. Good. Another useful lemma that we're going to use soon is that, again, the same condition. If you have a positive operator bounded from above by the identity, taking the value 1, then in this expectation value here, I can insert these operators x on the left or on the right of my state, and that doesn't change anything. So that's going to be very useful later. We'll see that soon. So the proof of this is basically an application of the Cauchy-Schwarz chord. Good.
Sorry, can I ask the lattice, is it finite size or boundary?
No, I'm going to assume it's an infinite lattice. So I'm only working on the infinite lattice. Yes.
So it's like the setup that we had in
yes, exactly. Yes. Yes.
Sort of quasi-level.
Yes, the quasi-level. Yes. Right, so maybe I'll come. So you mentioned boundary conditions. So I'll maybe come back to this soon when I say. I don't forget. I will say a little bit about that. Right, but I want to. This is the kind of the main result here in this setting, and that says the Tor code is unique for station-free ground state omega 0, and this state is pure. So maybe let me say a few words about this. So first, in particular, this for station freeness. So what does it mean? Well, our Hamiltonian consists of many different terms, and as we saw before, the ground state sort of minimizes the expectation value on all these the whole Hamiltonian. So it's the lowest energy state and the expectation value of the local Hamiltonian, that's kind of actually the energy. Right, so in general, the minimum does not necessarily minimize each of the terms in the Hamiltonian, but actually if it does, we call the state for station. So these are somehow the easiest ground states that you can have because they can minimize the whole state locally. Right. And I maybe should specify one thing here. So the uniqueness here, this refers to the for station-free ground state. So there are other ground states of the model that are not for station-free. Right, and this comes back to this comment from before on the boundary conditions, namely you can choose different boundary conditions and then let the boundary go to infinity. You can get different ground states, and you will get to different ground states. Right, so I have a nice paper on this with Bruno and with his former student Matthew Cha, where we do that. But yeah, so we'll mainly be considering this state. So besides the property that's for station free, it's also the only ground state that's translation invariant. So that's also a nice property.
Sorry, I kind of missed what frustration free means.
Yeah, so frustration free means it minimizes each of the terms in the local Hamiltonians individually. Yeah. Right. So it comes here in the proof as well. Right. Good. So one thing that we can show, this is maybe a little exercise, is that there's a state on my system such that it takes the value omega. Well, take the value 1 on all these star and all these packet operators. Right, there are different ways of seeing this. So you can, so one way of doing it, for example, is you can just look at the kind of a Boolean algebra generated by the AS and the BP, and then just, it's a Boolean, so you can just take, it's like you basically get the Ising model, so you can get a state like this and then extend it by Haan-Banach to the whole system. For example, what's slightly more work is to show that this actually uniquely determines the whole state, these conditions. So that's a little bit more work. It's not too difficult in the end. You really, what you do is you can take an A that's just a product of Pauli matrices, and you can insert this AS and this BP on both sides of the equation if you want, by this condition. And then you just use commutation properties of the Pauli matrices. So if there's something that if A anti-commutes, so then you get that omega of A is minus omega of A, so it must be 0. So basically, what you have to do, you have to find out, which cases does A commute, which case does anti-commute. This will get you the thing. So that's kind of a brief sketch of that. So I mean, not say too much about that. But yeah, by our previous results, we get a pure state. Good. The other thing that we have, and it's the precision freeness property, is that the expectation value of these operators is equal to 0. So why does it mean it minimizes each of these states? Well, this is proportional projection, and the eigenvalue of these things are 0 and 2, because I have to normalize this. So if this is 0, that's the lowest possible value, because these are both operators. Good. Now the last thing that we have to show that it's actually a ground state is this condition. Of course, Bruno's convention is different from mine. So Bruno put the so I put an I inside the delta, so now I have to get an I here to get rid of this again. So Bruno defined it with the I in another place. But otherwise it's the same thing. It's just the commutator with the Hamiltonians. Right. So well, we have to show that this is positive. So we can just work this out here. You get these terms with all this BP. And maybe I should say that. So here we have an infinite sum, but because if A is in the domain of delta, so it's not local observable. So for most of the terms of these sums, A will commute with this AS. So then these and this will drop out. So if A is a local observable, you only get finite sum here. That's what I want to say. Right. So using this lemma again, we can get rid of this one. We are left with this term. And this is a positive operator. So this whole thing is a positive operator. And because omega 0 is a state, this is positive. And that's what we have to show. So this is indeed a ground state. Good. So yeah, this is the state we're going to work with for the rest of the lectures, basically. But yeah, let me first make a comment. So first of all, why is this thing called the Torah code? Well, so originally it's defined on, well, you can define this model on basically on any surface. And if you define it, for example, on a torus like this, we have when you have non-trivial topology in general, this condition that they had before, that the state takes value 1 on the AS and the BP operators, it doesn't fix the whole state anymore, but only locally. So what does it mean? If you have an observable that doesn't sort of wrap around the torus, so that's what we mean with local in this context, then this condition completely specifies the excitation value. But now there is some freedom. If you take an operator that goes around the torus either this way or the other way, there's a freedom that doesn't so this doesn't determine the ground state. Of course, the proof that it is a ground state is that any state with this property is a ground state that's still the same, but this does not completely fix the ground state anymore. So in particular, we get a generacy, and for the Torah code, it's given by 4 to the power of G, where G is the genus of the surface that you define it on. Good. So this is a torus from Torah code, and the other property that is a fixed state locally, but not globally. Another way of saying this is that's actually a quantum error correcting code. So this is basically the property that to change the ground state, to get to a different ground state, you need something that's sort of non-local, that kind of wraps around the torus. Otherwise, you cannot go to a different ground state. So so the idea is that the quantum errors, they're local in nature, so they would not be able to get you to the different ground state. I think I'll maybe say a little bit more about this at the end of the week if I get time for it. But this is where the name comes from. That's so maybe one more interesting sort of comment is that right. So here you can imagine that maybe some interesting topological features going on. But actually, many of these things you can already recover in the SVSLC in the infinite Pareto limit, even though the topology in that case is trivial. Maybe remarkable. Good. So we will use omega 0 throughout as a reference state. So if you've done any quantum field theory, so you can think of omega 0 as a vacuum state, or kind of play the same role. Right. But the thing that's important for us is that once we have a state on a C-star algebra, there's something called the GNS representation. So I will not give you the definition here, but this is basically a construction that will give you a representation, well, a star representation of our algebra. So just a map from our C-star algebra into the bounded operators on some Hilbert space. So I should have said this. So H0 is a Hilbert space, omega is a unit vector in the Hilbert space, and pi 0 is a star representation here. Right. It has some nice properties, namely, if I act with my representation on this vector, I get a dense subspace of the Hilbert space. And finally, this is the inner product in the Hilbert space. As a mathematical physicist, my inner product is going to be linear in the second variable instead of in the first variable. But yeah, so if we act with pi 0 and a on this vector, and I take the inner product with the vector itself, I get back my state. So the state is implemented in this Hilbert space by this vector omega. So I should say one more thing that I forgot to write down. But this representation is unique up to unitary equivalence. So if you have another representation with these kind of properties, so another representation with a vector that implements the state and this density property, then there's a unitary between these two representations that interplays them. Good. Another property that we're going to use a lot is because the quasi-local algebras, we defined it in terms of this this matrix, well, the limit of matrix algebras essentially. So this is what's called a UHF algebra. And one of the nice properties about these things is that these are simple algebras, meaning every non-trivial representation is going to be injective. So you can always identify this image with A. That's more of a notation question. And with this notation in our ground state, we have this property that if I act with the star operators or the packet operators on this ground state, I get the ground state back. And in particular, this implies that if I act with the local Hamiltonians on this ground state, I get 0. So it's the lowest eigenvalue there. Good. So this is really just restating this property that I said before, that if you have omega 0 of A is the same as omega 0 of A times AS, etc. So I can just put this one in here, and then I get the property. Good. I said before I'm interested in states with a spectral gap, so gapped quantum states. So I can maybe make this a bit more precise here. So it turns out that if you have this C-star dynamical system, as we know, mentioned, you have a ground state of that, then you can implement dynamics on this Hilbert space by some unbounded operator, operator H. So this is now an unbounded operator on the Hilbert space. So morally speaking, it's just the limit what you get if you just take the sum of all these, well, take the local Hamiltonians, you just go bigger and bigger. So this will give you an unbounded operator, and that's more or less what this H is. So what do I mean with a gapped ground state then? Well, I just mean that this unbounded operator, which I can always normalize such that the ground state has 0 eigenvalue. But I'm going to assume there's a gap in the rest of the spectrum between 0 and the rest of the spectrum. So in this case, you can actually work out what it is, and it turns out to be equal to 2. Good. So the precise value is not important, but there is a gap between 0 and the rest of the spectrum. Right, and this gap is actually stable. So if you perturb this model with some perturbation that's not too large, the spectral gap stays open. That's quite a special property in general. That's going to be true. I will say a little bit more about this at the end of the week. Good. Right, we were interested in our anyons, so let's talk about them. Right, we have our routers again, and I can define 2 different paths. I can define a path just on the edges here, which I'll denote by blue. And I can also look at the dual lattice and define a path from the dual lattice like this. And to each path, I can assign operators. Right. So for these paths, I act with the Pauli Z matrix on each of these edges. And for the dual paths, what I do, of course, I have to act on where my system lives. So every time my dual path crosses an edge, I act with the sigma x Pauli operator at where it crosses, like this. Right. So to come back to this question earlier, does it matter if you choose a sigma x or sigma z in the definitions? The answer is no. Of course, if you make the opposite definition there, then you would have to interchange these two as well. So that's kind of like the main thing that you need to keep in mind. Good. So we have some nice properties here. Namely, these path operators, they always commute with the star. Well, almost always commute with all the star and packet operators. You can see that again, if they're away from each other, they discommute by locality. They act in different parts. If there's some overlap, in general, there will be an even number of edges overlapping. So again, you do this trick with anti-commuting twice, and you're back where you started. So there's one exception, namely if you are at the end of the path, because in that case, there's only one edge in overlapping, or maybe three. One or three, an odd number at least. So there, they anti-commute with star operators at the endpoint. So the xi and the xi hat, these are on the dual lattice, they anti-commute with packet operators. Right. So the interpretation of this is that if you act with this operator on the ground state, I get some anti-commutation with the star and packets in my Hamiltonian, and that means I will create some energy precisely at the endpoints. That's one way of thinking that. So some excitations. So these are typically called electric excitations for the ones at the star, or magnetic for the ones of the packets. You can see it in this way. If you act with the local Hamiltonian, so you act with this path operator on the ground state, and then with the local Hamiltonian, what you get is actually an eigenstate. And this is the number of endpoints of the path that's inside this region lambda. All right. So for each thing that's So basically, you get an energy of 2 for each of the excitations, each of the endpoints. So this is the picture here again, right? So here we act with the so these were the sigma z's, I think, and then so these are the sigma x. So here you get an anti-commutation. Here the same. Good. And of course, these. So we can think of these things because this here at this point is conditioned that there's anti-accommodation with this thing, so this will get some energy here. So we can think of this state as some excitation sitting here at this endpoint, and one at the other one, and the same for this one. So this will be an electric excitation, this will be a magnetic one.
So sorry, I see now the box always has 2 edges in common with the dashed paths, but I don't see how it works with blue paths. We seem to claim
this yes. So that can be an odd number, but these are both defined in terms of the sigma z's, I believe. So they always commute anyway. So they commute anyway. Yeah. So they can only commute with something of a different type. That's basically the thing. Yeah. Yeah. Thanks for the question. Right. So yeah, that's basically what I said before. If you choose one in terms of the sigma z's, you have to choose the other one in terms of sigma x's. Right. Good. So yeah, so these excitations, they're going to be your anyons. But you see this operator, they always create a pair because there's always, we have a finite path. So each of the endpoints, there's a pair. If you take a closed loop, you cannot get back in the back. Right. Good. So so that's the kind of the state picture. So for us, it will be more convenient to work in what's called the Heisenberg picture. So instead of looking at the state, I can look at this map by this. Right. So I don't really need a joint here. These operators self-adjoint, but in general, do need a joint here. But yeah, this is an automorphism, and this describes, how the observables change in the presence of these two excitations. I also have these two excitations, so if I would do an experiment, I would get some different outcome because the excitations are there. And this tells us how this changes. Right. But yeah, as I said, this is a pair of excitations. And well, we're interested in the single excitation because we're interested in the properties of the single anyons. So this is where it comes in very handy that we actually are in an infinite system, because now what you can do is we can send one of these anyons to infinity. So what does it mean sending to infinity? Well, I just choose my path longer and longer as follows. So I just choose a semi-infinite. So I call them ribbon, but that's kind of more necessary for the more complicated models. But here you can just think of an infinite for a path that's going all the way to infinity, and psi n is going to be the first n parts, so that's going to be a finite path, and I can just take this conjugation here and take the limit here to infinity. Right. So this is well defined. So it's easy to see if you look at the local observable, which are by definition dense in the classical algebra. At some point, this path will be outside of the support of this local observable, and because this path operators, they're very simple. They're just you just act with the sigma x on this edge. If there's nothing in between there, you just get sigma x squared at the end. So another way of saying this is that this sequence will become eventually constant for a local observable. So this converges, and then it's bounded, so you can extend it to the classical algebra just by continuity. Right, so that's the idea, and this is the picture that you should keep in mind. So we don't want this path to become too wild. This makes things easier. So we want to basically to go to infinity in a certain direction. And the way we encode this is by we choose like a cone on the lattice. Again, you can make this very precise, but this is what you should keep in mind. Just like some region that opens up a bit and goes to infinity. And you choose your path inside of this cone to infinity. Yes.
Question: what's special about this particular automorphism? Some particularly nice ones, but like.
So in this model, they precisely the automorphisms that create the single anion at the endpoints. That's why we define it like this.
How they look for them? If I didn't know them in the first place, what sort of
yes,
do they want from?
That's a good question. I will come to that. Later. Yeah. So in this case, I define it automorphism because I know what the model is. I know which operators create my excitation that I'm interested in. That's how you get automorphisms. But the whole goal of the superselection structure is to sort of abstract it, to do it in models where you don't know the answer. And I will come to that. Yeah. Good. Right. So that's the properties that I have. So one important property of this is that this automorphism is localized. That's clear from the description. If I take any observable outside of this cone, it acts trivially because of the commutation thing. It just get A back. Right. So I did it just for the path. Of course, you can do the same kind of thing for the dual path, which I will denote with this superscript X. And you can do a combination of these two. And that's so we have a dual path and a path, and they both go to infinity. Get so this Y is basically is the composition of this X type and this S type. So Y is called Y. Well, if you multiply power X with power Z, you get power Y up to a face, which you don't see here. Good. And then for notation, for a 0, I'm just going to use the identity map. So that's kind of like the trivial anion, if you want, which is no anion at all. Right. Good. So yeah, so we have this defined this map, and by the interpretation that I gave you, if I take the ground state and I compose it with this map, it describes a single anion state. So we have this single anion there, because the other one is all the way at infinity. We don't see it anymore. Right. Of course, this construction, this depends on well, this automorphism that I defined here. It depends on the choice of path that I chose to infinity. But it turns out there's actually a topological property, namely the state that I get here. It does not depend on the choice of paths that I chose, only on the endpoint. And there's quite an easy way to see this. So if let's say we have this path here, so the first part of this path, I can multiply with this packet operator, and as before, we can just insert them in our state from the left on the right. And if you look at this, if you multiply this path operators with packet operators, so now here I get the squares of the Pauli operators. So that's just the identity, and I get this new path, but now in a different way. So using this, multiplying with this path operators, I can deform my path in right amount. Something similar is true for the dual paths, but you have to use the star operators. But yeah, so what you can see is if we take these different paths, I get the same state, and it only depends on this endpoint and the other one. The other one we get sent to infinity, so we will see. So it will only depend on this endpoint. Good. So we can write this just indicating the site instead of the specific path. So yeah, it's important that this row does depend on which way you go to infinity, but the state itself does not. That's important. Good. Right. So I want to get to simple selection sectors, and I have to say a little bit about the equivalence of states on A. Good. So this definition, I'll say two states. Let's define it just for pure states. We say they are equivalent if and only if the corresponding GNS representations are unitarily equivalent. That's when I call two states equivalent. So they can look quite differently from a local point of view, but this definition. Right. So we want to have a nice criterion to see, can we actually see if two states are equivalent or not? And this is a quite nice one. So two pure states on the quasi-local algebra are equivalent if and only for every epsilon bigger than 0, I can find some finite set lambda, such that for every local observable outliers outside of lambda, we have this inequality. So these two states are close to each other if I am just far enough away from this finite region. So I can choose some tolerance. I can find some finite regions which can be very big, but if I have any observable outside of there, I can distinguish them, then the states are inequivalent. So another way of saying this is that two pure states, they are inequivalent if and only if they can be distinguished at infinity. So if I just go far enough out of the system, I can distinguish the states. Good. Right. So I defined 4 different types of states now. So one was for the, this was just the identity, so that's the ground state. One where we had this X type going to infinity, one to the Z type going to infinity, and a combination of these two. And all these 4 different states, they are inequivalent states. Right. So yeah, so we can always move the endpoint around by a local operator. So if you just extend the path, that's very easy to see. You can always move the endpoint around. So and these are unitary, so this will give a unitary equivalence. So you can always assume that they start at the same point. Right. And then what you can do is you can right. So you need to take some finite region, and then you take a loop outside of this finite region. So you take close loop outside this finite region. You can check that this path operator you can actually obtain by the product of all these BPs, all the packets operate inside in this loop. So basically, if you do this, all the terms cancel out except at the outside. Something similar for the dual approach. Right. So we have this anti-commutation property, and then you can see if there's an endpoint in there of a different type. These automorphisms, they either act as the identity on this group operator or as minus the identity. So we get, if you compose with the state, that this is plus or minus the identity. Right. So when do we get a -1? Well, if and only if, right. So yeah, it's basically if you have, let's say, an X string, then if you go around there with the dual part, so say you have a path and you get around there with the dual part, you get a -1. So this different type of path can detect a different type of string. So yeah, so basically the point is that for each of these 4 cases, there's always each pair of states, there's always one group operator that detects that as excitation value 1 for one state and -1 for the other one. It's you just have to choose something that anti-commutes with the operator. So this is kind of basically what's known as Wilson loops. But yeah, the point is I can detect this excitation that's sitting at infinity. So that means if I have 2 different types, I can make this excitation value is always going to be 2, meaning these states cannot be equivalent. Right. So really the idea is that another way of saying this is that we have this excitation sitting here at this site, but we can detect it from arbitrarily far away as long as we are able to go sort of around this excitation with some loop operator. Good. Right. So I think in view of the time, let me go over this tomorrow. So this will hopefully answer this question tomorrow about how why do we choose these automorphisms. But yeah, so the point now is just to summarize here. So we have these 4 different types of excitations. For each of these different types of excitations, we have an irreducible representation, and all these representations they are inequivalent to them. So we have 4 different types of irreducible representations. And these, of course, are going to correspond to anyons. So basically, the rest of the week, what I want to do is I want to study the structure that you can put on this on the set of these representations, and we will see that we get our full modular tensor category in this case like that. So I think that's a good moment to stop, and I will continue with this tomorrow. So thanks.